Okay. So module 6. So module 6 is all equilibrium. So before you understand the concept here of this equilibrium, because this is one of the hardest thing to discuss. First, it is an abstract concept. So the way I usually discuss this topic is like playing a game. So I want you to participate in this by putting out your calculator. So assuming we have two boxes, the label R, wherein 1/2 of any items of label box R goes to box P, wherein 1/4 of any items goes to box R. So initially you have 40 items here, no items in P. So what is 1/2 of 40? You can
20.
say it. Yes?
20.
20. And then 1/4 of 0.
0.
Okay, so 1/4 of 0 is 0. Okay. So after the exchange, you have 20 here, you have 20 here, and then you continue the exchange. 1/2 of 20, 1/4 of 20. So 1/2 of 20 is what?
10.
So this is 10, and this is 5.
5.
Right? So you lose 10, you gain 5, you have 15. You lose 5, you gain 10, you get 25. Now, if you have a fraction, you're just going to round it off. Because remember, we're looking here as items. So hindi natin pwedeng hatiin yung item na yon. Because 1/2 of 15 is what?
7.5. 8
So 7.5. So we round it up. That's 8. And then 25, 1/4 of that is yung kinakainisan yung system sa UPLB, sais. Right? So at the end, you lose 8, you gain 6. So this is 13. You lose 6, you gain 8. This is 27. So 1/2 of 13 is what? 1/2 of 13 is
7.
6.5 or 7. And then 1/4 of 27 is around 6 point something.
6.5.
Okay, and you round it up, it's 7. So here you now have an equal exchange rate. So this one is 13, this one is 27. So the question is now, you reach the so-called equilibrium. Okay. Now the question that I have that I have to answer by yes or no. Is the 27 items here the same as the 27 items on this? Is the 13 items here the same as the 13 items on this? Yes or no? Okay. How are the others? Isa lang yung sumagot.
No.
May ibang nag-yes? Okay. So it's just a yes or no. Marami pa rin nagsasabi ng yes. Yes, yes, yes. No, no, no. The answer is no. Because 7 items of that is different before and after. Is that convincing enough to those who answered yes? That the 27 items here is different from the 27 here, and the 13 here is different from the 13 here, because there's 7 items that was removed and replaced by another 7 items. Okay? Convinced ba yung mga nag-yes that the answer is no? Okay? Now, how do I put this in what we call an equilibrium state? So when we're talking about equilibrium, this is the state at which there are no observable changes as time goes by. So similar to the activity that we have, we thought, okay, 27, 27, set 13, 13. So we thought they're almost the same. So there's no changes. But in fact, you have what we call a dynamic change. You familiar with the word dynamic? Saan nyo naririnig yan? Usually naririnig niyo yan sa leaders. Question here, is the Philippines have dynamic leaders at this present? I don't want to hear the answer. Bahala kayo doon. Okay. So, whenever you have chemical equilibrium, you have two conditions to meet. One is the rate of the forward and reverse reactions are equal, and the concentrations of the reactants and products remain constant. Did we meet it here in our activity? So the rate of the forward and the backward direction are equal. So we have here a 7 and a 7. And the concentration of the reactants and the products remains unchanged or constant. So you have 27, 27, and then you have 13 and 13. So we met the condition for a system at equilibrium. Okay. Now, what's the other thing that we need to assume whenever we have what we call a system at equilibrium? We need to have what we call a reversible reaction. Now, right now, what can we say about all the reactions that we have discussed? The reaction that we have all discussed is just like we say the name of the band, the name of a boy band. All of the reactions are what? Ano yung band na yun? Oh, alam nila. It's one direction. But if we're going to look all the chemical system that we have, there's only a few systems that goes one direction. Okay, most reactions are what we call reversible. So when we say reversible, once you produce the products, then if the products remain in the system, most likely it's going to go back to produce the reactants. Okay, so a good example that we have here, see that thing? Now in an open system, it will be a one direction. So once the liquid evaporates, it's gone. The gas form escaped. But when you close it, okay, once the system once the chemical or substance evaporate, what will happen? You produce the gas there. Now the gas, since it's just there in a closed system, after some time it starts to condense until such time that the rate of vaporization is equal to the rate of condensation. And you have there a chemical equilibrium. And that can be written in terms of this physical equilibrium. But you can always observe this in a chemical system like this one, N2O4 producing NO2. Now, if we're going to look at this, what we call chemical equilibrium, just like the activity that we have, there are different starting points. Now, in our activity, we started with what? 40 items in R, 0 items in P. But we can also start 40 items in P and 0 items in R, or 20 items in R and 20 items in P. But nevertheless, there will come a time that they will reach equilibrium. Okay, so if we're going to plot them, the activity that we have, so the X is the number of exchange, and this one is the number of item. So maybe we can start here with what? The 40. And then we start here with 0. So after sometimes you have this one. So you might do it like this, and this one will do it like that. So there will come a time that you reach a system where there's no changes in the reactants and the products, or the number of box P and box R. So the same thing in a chemical system. So dinitrogen tetroxide producing 2 nitrogen oxide or monoxide or dioxide, ano ba yan? Nitrogen dioxide. So you can start with just NO2. So whatever material that you have, it will be utilized, its concentration decreases while the other one increases. So you produce with, you started with NO2, it will be used up, its concentration goes down, while the N2O4 concentration goes up because it starts to produce. But after a certain time, the concentration remains constant. The same thing if you start with N2O4 instead of NO2. So it has a high concentration that will start to decrease. When it is used up to form NO2's concentration starts to increase. And at such time, their concentration remains the same. And they reach the so-called equilibrium state. This is also the same when you start with NO2 and N2O4. So one of them will give way. One will decrease in concentration because it's going to be used up, and the other one increase because that's the one that is produced. Different starting point, different concentration, initial concentration, different equilibrium concentration. But if you're going to look at the ratio of the concentration at equilibrium, there is a relationship wherein they will give you a constant value. And that's the equilibrium constant. Now, the equilibrium constant is based on what we call the so-called law of mass action. Okay, so in an equilibrium constant expression, what you have there is just you write whatever you can find in your product side raised to the coefficient, divide it with whatever you find in the reactant side raised to the coefficient. And that is the basis of your what we call law of mass action. So if you're going to look at general equation, you have A of A, B of B, so A and B is the coefficient. C of C plus D of D, they are both the coefficient. So when you're going to get the K, it's just C raised to the C times D raised to the D divided by A raised to the A times B raised to the B. The products of the products over the products of the reactant. And this is your law of mass action. So that is the basis of your chemical equilibrium expression. Questions so far? Huwag mo yung magtanong. Libre ang magtanong. May tanong? Now, what information the K value convey to us? So if you're going to look at this, K is just simply the ratio of the products over the reactants. If there are more products over the reactants, the K value is more than 1. And what does it tell us? If the K value is more than 1, it lies to the right side. You're going to have more products, or it favors the formation of the products. Okay. Now, if K is more than 1, so mostly we could say the numerator is greater or bigger than the denominator, like this one here. But if it's the other way around, it means there's less products compared to the reactants. It favors the reactants, like this one. That's the information that you can get with the K value. So if you're going to go back here, there's a K value that you have here. So based on this information, to which direction is the reaction favored? Sige nga. So those are the type of questions that they have usually in the exam. Given this information, which of the following is true? Okay? Papahirapan. Which of the following is are true? So A, B, C, D, or 1, 2, 3, 4, and then A and B, 1 and 2, B, 2 and 3, some sort of that. So in this type of reaction, the one that is favored is in the backward reaction because the number that you have is less than 1. Okay? Now, so far what we have discussed here are homogeneous equilibrium where in all phases are just the same. So in this reaction that we have, all of them are in gaseous form. So this is what we call homogeneous equilibrium. Now, since this is in gaseous form, you can express them other than Kc. You can express them in terms of Kp. So we use the partial pressure, okay, instead of this concentration. So what do you think the C here stands for? Ano yung C na yun? C is for what? Constant? Concentration? Okay, the C stands for concentration. It's not constant, it's concentration. This bracket refers to molarity. Now, Kc is equals to the ratio of the products over reactant in terms of concentration. Kp is equals to the ratio of the partial pressure of the products over the partial pressure of the reactants. But Kc is not equals to Kp. The relationship between the two is this one, wherein Kp is equals to Kc times RT raised to the N. And you define N as the number of moles of the gaseous product, the total number of moles of gaseous product minus the total number of moles of the gaseous reactant. So what is delta N for this system? Anyone? What is delta N? So you have here 2 and you have here 1. So 2 minus 1. So that is equals to 1. Okay? We're going to talk about it. Yan yung nagpagising sa akin sa klase kanina. So if you're going to look at this, this is just the sum of the coefficient C and D minus the sum coefficient A and B. Now, another way to look at the homogeneous equilibrium, if it's not what we call gas, is the one that you have in aqueous solution. So for instance, here, this is acetic acid with water producing acetate and hydronium ion. So as you could see here, this is liquid, but this one is aqueous. So if you follow the law of mass action, so the law of mass action just lists all these species involved. But you have to take into consideration that if you write it in terms of equilibrium expression, not all species are going to be written. Some of them, like water, is a constant. So you don't write that. Okay? So if you're going to write the correct equilibrium expression, then you're going to remove water. So general practice also that you're not going to include any units for the equilibrium constant. So we could say Kc is just a ratio of the products over the reactant. It doesn't have any units. Claro ba? So far, so good? So as I said, in the equilibrium expression, there are some limitations to which you don't include or to which you can include. And the one that you can include is either the gaseous form or the aqueous form. So if you have a liquid and later on a solid, you cannot include them in the equilibrium expression. Clear? Now, let's go on some problem solving here. So the equilibrium concentration for the reaction between carbon monoxide and molecular chlorine to form COCl2 at 74 degrees Celsius are the following: 0.012, 0.054, and 0.014. Now calculate the equilibrium constant for Kc and Kp. So which do you think we can calculate right away here? The Kp or the Kc? We're going to use the Kc because the concentration is the one that is given. So the first thing that we're going to do is to write the reaction. So this is the reaction. Now, what do you think is the delta N? Dito na kami nagkatalo kanina. So by the time you're answering what's the delta N is, so we're going to write the equilibrium expression. So Kc is equals to what? COCl2 divided by CO over CO times Cl2. So this is what you have. And then what you're going to do is you're just going to substitute the given number there, and you get the value of 216, but you round it up to two significant figures. That's around 2.2 times 10 to the 2. So what is the value of N? Sige nga. So if you're going to look at this, you count this one here. So this is what? 1. This is 1 and 1, giving you 2. So 1 minus 2 is equals to what?
Negative
Very good.
1.
Negative 1. Kasi yung klase kanina, hindi alam ko anong sagot eh. Natawa yung anak ko. Yung 7-year-old na anak ko. Okay? Because we need that to get the Kp. Now, before we solve it, when do you think Kp equals to Kc? Anyone? Is there a situation wherein Kp is equals to Kc? Yes or no?
If the delta N is 0 po.
Okay. Yes. There's a chance that Kp is equals to Kc when your delta N is equals to 0. Because what happened, if you have RT raised to the 0, that is equals to what? What is any number raised to 0 equals to?
1.
1. So Kp will be equals to Kc. But in this case, that's not the case. That's a negative 1. So we're going to put the value here. So we end up maybe writing this as what? Kp equals to Kc over RT. Right? So you can write it in this form, but this is just the same as that. Agree? Na itong form na to, pareho lang sa form na to. Raised to the 1. Tama? R is the gas constant. So there's two common value of the R. One that is used for energy calculation, which is 8.314, and one for the non-energy calculation, which is 0.0821 liter atmosphere K mole. So you should, although there's no calculation, I think of the R in the exam, but R is a gas constant. Question. So we have a Kc that is equals to 220 and a Kp that is equals to 7.7. Tanong. So let's go here. May tanong ba? Meron natin may tanong. Yung R is a gas constant. So if it's a constant, it's given. Okay. I would suggest just play with the significant figure rule, just to be safe. So the next problem that we have, so you're given the equilibrium constant Kp for the reaction 2NO2, producing 2NO plus O2 minus, or O2, okay, is 158 at 100 Kelvin. So what is the equilibrium pressure of O2 if the PNO2 or partial pressure of NO2 is 0.4 and partial pressure of NO is 0.270 atmosphere? So what is the delta N here? Before we solve the problem, ano yung delta N? Anyone?
One.
Okay, so it is equals to 1. So you have here 2 plus 1, making it 3, minus 2, giving you 1. Now, we're going to solve partial pressure of oxygen. So if we're going to express the equilibrium expression here in terms of partial pressure, so we have P2, partial pressure squared of NO, partial pressure of the oxygen divided by partial pressure of NO2 squared. And then we fill up the one that we know. So if you're going to look at this, this is the one that we're looking for. So what we're going to do is we just multiply this with this over this on both sides. So that cancel out and this cancel out, giving you PO2 equals to Kp times P squared, PNO2 squared over PNO squared. So you substitute it with the given value and you get 347 atmosphere. Now, we said Kp is equals to Kc when delta N is equals to 0. Now, when does it happen when Kp will be more than Kc? And when does it happen that Kp is less than Kc? Sige nga. So if you're going to look at the condition that we have right now, Kp is greater than Kc, okay? But we didn't get the Kc value yet. So what do you think is the Kc value there? So we're going to look at Kp equals to Kc RT delta N, right? Tama ba? So to get Kc, we're going to divide both sides by RT raised to the n. So we have 158 divided by 0.0821 times you have 1,000 here raised to the 1. So what is the answer that you will get? To see the relationship here, wherein delta n is positive. Anong sagot? You will get 1 point. So there's 3 significant figures that you have there, so it's 1.92. So we could say Kp 158 is greater than Kc. So delta n is what? What's the value of delta n for that to happen? Positive or negative? That is a positive. Now, when does this thing happen? So I think we have a condition, the previous one. So look at here. You have a Kp and a Kc. So the Kp is what? 7.7. And the Kc is 220. So this is a condition wherein we have a negative value of delta n. So we could say Kp is less than Kc when delta n is negative. Okay? Questions so far? Tanong? Now, what happened if the system that you have is not homogeneous? If the system that you have has more than different phases. So in that case, you're going to have what we call the heterogeneous equilibrium. And you're going to apply the same principle as we have in the equilibrium expression, wherein you only include the gas and the aqueous system. Okay, the gas species and species in aqueous form. So for instance, if you have here, you don't consider solid portion or the solid phases in the expression. Although the law of mass action will write all species that are present, if you're going to write the equilibrium expression, it's just CO2. Okay. And since this is a gas form, you can also express it in terms of Kp. Now, whenever you write the delta n, you will only consider the one that you can write in the equilibrium expression. Now, my question, what's the delta n value here? Anyone? No, it's 1. Now, where did you get the 1? From 2 minus 1 or 1 minus 0?
1 minus 0.
Okay? The others. Where do you get the 1? 2 minus 1 is equals 1. 1 minus 0 is also equals to 1. But which is the correct one? Okay, the answer is, as I have told you only include in delta N the one that is included, the species that are included in the expression. And in that case, it's just CO2 minus none. So this is the reason why is it 1. 1 minus 0. Yep. Since it's a constant, it's not included in the equilibrium expression, you're not going to include it in the delta N computation. That's why the one that you get there is from 1 minus 0. Is that clear? And also remember that the concentration of the solids and pure liquids are not included in the expression of the equilibrium constant. Okay. Now, to give you further the explanation why the solids are not included, so maybe you can look at the system itself. So this is how it looks like. Okay, so you have calcium carbonate and calcium oxide, and you have the carbon dioxide. If you're going to look at this, the pressure is just due to the carbon dioxide. So any changes of the pressure that happens there, it's due to the changes in the concentration of your CO2. So the concentration goes up, the partial pressure goes up. If the concentration goes down, most likely the partial pressure also go down. Okay, so the CaCO3, calcium carbonate, and calcium oxide remains the same. Now let's look at this one. So you have this ammonium hydrogen sulfate. So it's a nasty combination. Okay, the smell of the restroom and the smell of a rotten egg. Try to imagine that combination. So the partial pressure of each gas is 0.265 atmospheres. So calculate Kp and Kc. What is delta N?
Two.
So delta N is equals to 2. So you have 1 here, 1 here, and 0 here. So that's 2 minus here. Now, if we're going to look at this one, which one's the first we're going to calculate? Kp or Kc? Which K? It's all about that K, all that K. So since the one that is given is in atmosphere, the first K that you're going to calculate is Kp. So you write the expression, Kp is equals to the product of the partial pressure of NH3 and the partial pressure of H2S. And since they're the same, you just square 0.265. And from that, you get this value. Now, Kc. Let's apply the concept that we learned. What do you think the relationship of Kp here with regards to Kc? Which one is bigger before we answer the question?
Kp.
So based on our conclusion before, since the product is more than the reactant, that means delta N is positive, okay? Kp is greater than Kc. So we can solve for this. So we can have this expression to see how different this one with that one. So here what happened is just Kc is equals to Kp over RT raised to the delta n. It's just the same as that. And if we're going to change the value that we have here, so this is the value, which is indeed less than 0.0702. Analyze, check. And if you have question, don't hesitate to ask. Question. The answer is no. You cannot have a negative Kp or Kc value. Remember, they're what? Ratio. So you cannot have a negative ratio. Is that clear? So if we're going to continue, let's look at this sum of two reactions. So when you have a reaction where you have A plus B producing C plus D, giving you a certain K prime value, and another reaction, C plus D, producing A plus F, giving you a K prime value. So if you're going to look at the equilibrium expression for the first reaction, it looks like this. And for the second reaction, products over the reactants looks like this. So if you're going to add the two reactions, you will see that you can cancel some of them that are common in both sides, the C plus D. So you have this one. So the new K that you have is just the product of Kc prime times Kc double prime. You just cancel here the C plus D. Okay? So the new K that you have there is just the product. So please don't confuse this with Hess law. What is Hess law? If you remember, if you watch the short video, what is Hess law? So in Hess law, you have the enthalpy. So if you add the reaction, the new enthalpy or the enthalpy of the resulting reaction is just the sum. But that is not true here. Okay. So what you have here, the new reaction is just equals to what? It's delta, its K is just equals to the product of the K of the reactions that were added. Are we clear on that? Klaro ba? Baka mamaya magkalituhan gamitin ito sa Hess law. So this is not Hess law, okay? Hess law involves enthalpy, this involves equilibrium constant. So the wording that we have here, if a reaction can be expressed as the sum of two or more reactions, the equilibrium constant for the overall reaction is given by the product of the equilibrium constant of the individual reaction. Hess law would say the sum of the enthalpy of each reaction. So I want you to know the difference, okay? I don't want you to interchange them. Are we clear on that? Baka magkagulo yung utak nyo sa exam sa Friday. Oh. That's why I'm not going to make available this recording until you're done with your exam. Question? May tanong? So the next thing that you need to consider is if you have a reaction like this, so the K expression that you have is product over reactants, and this is the value. Now, if you reverse the reaction, the new K will just be the reciprocal. Again, sa Hess law, ano nangyayari kapag ni-reverse natin yung reaction? What happened in the Hess law if we reverse the reaction? Anyone? Are you still with me? Okay, in the Hess law, when we reverse the reaction, we change the sign of the enthalpy. But, okay, here, in equilibrium expression, when we reverse the reaction, the resulting or the new K is just the reciprocal of the previous K. So, klaro tayo doon? Huh? So when the equation for a reversible reaction is written in the opposite direction, the equilibrium constant becomes the reciprocal of the original equilibrium constant. So far, what we have learned is summarized in this slide. So the concentration of the reacting species in the condensed phase are expressed in molarity. In the gaseous phase, the concentration can be expressed either in molarity or in atmosphere. So Kc or Kp. Now the concentration of pure solids, pure liquids, and solvent do not appear at the equilibrium constant expression. The equilibrium constant is dimensionless. It doesn't have any unit. And if you have observed in quoting the value for the equilibrium constant, you must specify the balance equation and the temperature. And if a reaction can be expressed as the sum of two or more reactions, the equilibrium constant for the overall reaction is given by the product of the equilibrium constant of the individual reaction. So question so far, before we go in solving a more complicated problem. Tanong? So we're not going to discuss this. So let's go now to Q, the reaction quotient. This is similar to K. Q is also the ratio of products of the reactants. The only difference between the two, Kc would involve a system at equilibrium, while reaction quotient of Q, you look at it at different condition or at different time, usually initial concentration. Okay, and the information that the Q conveyed to us is what we need to do for the reaction to proceed equilibrium. So all we need to do is look at the Q value and compare it with the Kc value. So if the Qc is greater than the Kc, the system would proceed from right to left to reach the equilibrium. Now, if both QC and Kc are the same, you have a system at equilibrium. But if the QC is less than the Kc, so what you're going to do is you need the system to proceed from left to right to reach the equilibrium. So this one is here. Okay. So if the QC is this one, QC less than Kc, so this one is supposed to be this one. Okay, so the system must proceed from left to right. Now QC greater than Kc, which is this one. Okay, so the system would proceed from right to left to reach the equilibrium. So what does it tells us is, it tells us the status of the reaction and at what direction you need to move to reach equilibrium. So usually Q, determination of Q is just being done if you have problems wherein you're given the initial concentration and you are asked for the equilibrium concentration. And there's a step for you to follow in calculating equilibrium concentrations when the initial concentrations are given. So far, the problem that we solved so far are given the equilibrium concentration. Then what if instead of given the equilibrium concentration, you are asked to solve it, and what are given instead are the initial concentration. So how are you going to do that? There are steps that you need to follow. Okay, so you express the equilibrium concentrations of all species in terms of the initial concentrations and a single unknown x, which represent the change in concentration. And then you write the equilibrium constant expression in terms of the equilibrium concentrations, knowing the value of the equilibrium constant, solve for x, and having solved for x, calculate the equilibrium concentrations of all species. So I will show you how to do this step by step. Okay, how you solve for x, or how do you equate let x equals 2. So usually a problem similar to this is like the one here. So you have this system, and then you're given K, you're given the initial concentration, and you are asked to solve the concentration at equilibrium. So usually the step that you're going to do here, you let x be the change in the concentration of Br2. Okay. So you have the Br2. So that is the reaction. And then you put the initial concentration. So it's given. So you have 0.063, okay, and 0.012. Now here is the one where you get the Q value. So what is Q equals to? So we could say that's Br squared over Br2. And we change the value that we have there. So you have 0.012 squared over 0.063. So as you could see, it's the same as K. The only difference is it's not a system at equilibrium. It is the initial concentration that you have. Klaro ba yun? Now, what is the value of Q here? Because you're going to compare the value of Q with respect to K. Try to calculate. What is Q value? Q is equals to 2.29 times 10 to the negative 3. So what is the relationship between the two, QC and KC? Anong relationship ng dalawa? QC less than KC, QC greater KC, QC equals KC. So QC is greater than KC. So saan direction mapupunta yung reaction? Okay? So it favors the left. So when QC is greater than KC, it favors the reaction from right to left. Is that clear? Now, we go to the other part that we have. So that's the initial one. So what's the changes that we have? So if you're the reactant, you're going to have X amount that is used up. And if you're the product, you're going to form 2x. Well, 2x because you have the coefficient of 2 here. So that's plus 2x. Now, when you have equilibrium, all you need to do is bring down what's the initial and the changes. Yun yung difference ng ano dito. So ito, sum lang to ng initial tsaka change. Same thing with this one. And what you're going to do, okay, this is what we call the ice table. But here in the US, I call it the rice table because I'm Asian. So yung R na naglagay dito, okay, for reaction. And this is very useful in establishing the system that you have. Because once you have the table, you can use the value that you have in equilibrium to replace in the equilibrium expression. So yung BR raised to the 2 doon, you replace it with 0.012 plus 2x squared and divided by 0.062 minus x. And you have this relationship that you have. Now, this is a little bit complicated. So what do you need to do? So from that expression, you have to solve for x. So you have to arrange it in what we call quadratic expression. And once you have the quadratic expression, ax squared plus bx plus c equals to 0 like this one, you have to solve for x using the quadratic formula. And there's always 2x values that you get. So it's either the negative 0.05, 0.015, negative 0.0105, and negative 0.00178. Now, which do you think is the correct x? Both of them are negative, but both of them are possible. So what do? You use it in the expression. Okay, so ito yung ice table mo. So as you could see, you can use it to subtract with this one. Okay, or you can use it to subtract with that one also. Now, if you're going to use this value, Okay, ang makukuha mong value sa 0.012 plus 2x is this one. And the other one, if you're going to use it here, you're going to use this one. So which is the correct x? The first x or the second x? When you get the values here, these are what you get. So is it the first x or the second x? So the answer is, okay, the second x, because you cannot have a negative concentration. So that's the correct one. And you're going to use that to subtract in this one. And once you do that, you get that amount. Now, how do you check if this is indeed right? So you're going to use the expression 0.00844 squared divided by 0.0648. So this should be equals to what? Just try. Try. Ano nakukuha nyo? So you have what? 1.01. So isn't that what your K is? That's the way for you to double check if your answer is right. Tanong. So the change is if you are the reactant, that's minus x. Kung ito 2Br, that is minus 2x. If you are the product, that's plus x. So depending kung ano yung stoichiometric coefficient mo, you're going to put that number. Minus x for the reactant, or minus 2x, or minus 3x, kung ano man yung coefficient. And then plus x, okay, kung ano man yung coefficient ng product. Tanong, because that ends our lecture for today. The next part that we have is the Chatterley's principle. I think we have 20 minutes of that time next meeting. So question. Question which regards to equilibrium. Tanong? Question before I turn off the PowerPoint and the recording. So tanong. No, there's only 23. Next week, we're going to have quiz every meeting because I don't want the number to go down. So bibigyan ko lang kayo kasi exam this week. But once it goes over less than 20, I'm going to implement quiz every meeting. So question?